my pleasure to introduce you to Jonathan Gagne, if you have not already met him. Jonathan is from Quebec, and he did his bachelor's all the way through his Ph.D. at the University of Montreal. Although he did take a year off from that to go on a IPAC graduate fellowship to the Infrared Processing and Analysis Center in Pasadena, California, and work on a completely different project having to do with the infrared radial velocity detection of planets, before going back and finishing his PhD in Montreal, working on mainly finding the kind of projects you'll hear about today, finding low mass objects that are young and in the solar neighborhood. He got his PhD in 2015. He was awarded both a Hubble and a Sagan Fellowship, and we persuaded him to choose the Sagan and bring it here to DTM, where he's been looking forward to using Magellan to do lots of follow-up on these neat young objects that you'll hear about. And not only did he get NASA's, or astronomy's, 2 prestigious fellowships, he also got a separate research grant from the National Research, what is it called? National Research Council of Canada in English, and something with other random letters in French. CRSNG. Right? Yeah. So Canada rewarded him with a separate research grant to be able to spend on pursuing his research. So as you'll see, he's been incredibly prolific and has lots of new and exciting results to share with us. So
thank you. Just let me open my mic. Okay, thank you for having me. So I'm going to present you the BASS-Ultracool project, which is the continuity and upgrade of what I did during my PhD. So I'm going to try to answer 4 fundamental questions of astronomy. So there are 4 of them that I'm particularly interested in. The first one is the initial mass function at very low masses. So this is simply the number of stars at every given mass that you get when you form stars from a molecular cloud. And then I want to try to understand better the properties of gas giant planets. I want to build templates of high signal-to-noise and high-resolution spectra for empirical planetary-mass objects, so that the exoplanet people can use empirical data instead of models. And I want to try to address the question, are ejected planets rare? So this is a more distant goal because it's a very hard one, as you'll see in the next slides. And the methods I'm going to use to answer these 4 questions is these 4 methods, which is really just one method. So finding young brown dwarfs in moving groups of the solar neighborhood is able to bring elements of answers to all of these 4 questions. So I'm going to explain to you pretty much every word in this sentence. So that's going to be the first section of my talk. I'm going to introduce you to brown dwarfs, how the young brown dwarfs are special, and what's a moving group. Then I'm going to move on to explaining the Banyan 2 tool, which is a statistical tool that I developed to find members in moving groups, and the BASS survey, which was mainly my PhD project. So then I'm going to move on to explain to you the new project that I call BASS-Ultracool, and I'm going to finally present you some new discoveries and my future plans for this project. So what's a brown dwarf? Very often you're going to hear that they are either failed stars or super Jupiters or just objects in between stars and gas planets. So you can see that in this absolute luminosity versus age diagram. So the objects to the top here are stars because they fall on a main sequence after a few million years. And brown dwarfs that have masses lower than around 80 times that of Jupiter, they never fall on a main sequence. So they continually cool down and get fainter with time. Planets are kind of similar to brown dwarfs in that characteristic. However, they have masses even lower than 13 times the mass of Jupiter. And the main difference between those is that in brown dwarfs, there's a very early and short phase of deuterium burning that doesn't allow them to really get on a main sequence. It just starts to stabilize and then there's no more deuterium left to burn. So one important factor of brown dwarfs is that they contract as they age. So this is also an effect that they never fall on a main sequence to get a stabilized radius over large periods of time. So the very young brown dwarfs are going to be much larger than the older brown dwarfs. So try to keep this in head for the following slides. So these two effects, I'm going to go back to the first plot just to crystallize something. If you take an object that is very young at a fixed luminosity or temperature, the younger object will effectively be a lower mass object. So you could look at two objects that have the same temperature and luminosity, but they could have two very different masses if they have very different ages. So this, combined with the radius argument, conspires in yielding a lower surface gravity in the younger brown dwarfs. So if you have a very old brown dwarf at a fixed temperature, it's going to be contracted, and it's also going to be a more massive brown dwarf. So both effects are going to give it a larger surface gravity. So one of the most differentiating characteristics of young brown dwarfs is their surface gravity. So as you can see here, I'm plotting the surface gravity as a function of age, and all these tracks are fixed temperatures. So if you go to a younger age, you go to a larger surface gravity. So now I'm going to talk to you about the photometric properties of field and young brown dwarfs. I'm going to use the term field to designate all brown dwarfs that are just members of the field of the galaxy, so just old brown dwarfs. So you can interchange field and old in all the sentences I'm going to use. So if you look at only the old brown dwarfs, or the field brown dwarfs, you can see that the J minus K color, this is a near-infrared color, gradually gets redder and then comes back to bluer colors at a given spectral type. So the spectral types here, if you go to the right, they correspond to colder objects. So if you fix the age, those are going to be less massive. So we call them later type. So the young objects are the ones plotted in red on that figure. So you can see that at early spectral types, or for warm objects, the near-infrared colors are pretty similar between the two populations. But as you move to later type objects or colder objects, the young objects clearly get redder. And then if you look at the absolute brightness in the J-band, there's kind of a different trend. If you look at the warmer objects, the young ones are brighter, and the colder ones become similar and even fainter than the old brown dwarfs. So the larger luminosity is expected because they have an inflated radius. So remember, the young objects have a larger radius, so they're going to have a larger absolute brightness. However, as you move to the later spectral types and the cooler temperatures, the clouds become very important in young objects. And this is an effect of their surface gravity being lower. Because of this, you get thicker clouds higher up in the atmosphere, and this counterbalances the larger radius in J-band. This is mainly because the clouds are going to move the flux from the J-band to longer wavelengths. So as an effect, the larger radius and the thicker clouds compete against each other, and then at cooler temperatures, the clouds start to win the battle, if you wish. And then these thicker clouds also explain the redder J minus K colors. So as I was mentioning, the clouds move the flux from the J-band to larger wavelengths, and K-band is one of those larger wavelengths. So you get a much redder slope if you have thicker clouds in the high atmospheres. If you look at absolute J-band brightness as a function of color, you see some very interesting trends. This is kind of a very important plot in the domain of brown dwarfs. So if you look at field brown dwarfs, you see that they get fainter and redder as the temperature is lower. But then when you go below a certain temperature, there's a huge reversal. And actually this whole thing happens in a quite narrow range of temperatures. So this corresponds to a dramatic change in the atmospheric properties of the brown dwarfs. Mainly, it's not, we haven't all figured out all exactly what the effects are, but there are many effects that have been proposed for that. One of them is that the clouds break up and form larger holes, and at some point the clouds even go below the photosphere so that you stop seeing them if you do photometry or spectroscopy. Another effect that kicks in at these temperatures is the visibility of methane in their spectra. So all of this happens in a very narrow range. So this is, remind you, those are the old brown dwarfs. So as they are cooler, you see this drastic reversal to blue J-K colors, and then they just keep fading to fainter absolute brightnesses when you go to lower temperatures. So if you plot the young brown dwarf sequence on top of that, you can see that it's all shifted to the right with respect to the field sequence. And this is both an effect of the early objects being brighter and the late type objects being redder. So this all moves the sequence to the right on that diagram. Some of the distinguishable elements in the spectra of old versus young brown dwarfs are, for example, the peakiness of this band here, which we call the H band. You can see that young objects have a much more triangle-shaped continuum. And there's also the iron hydride absorption here, which is much weaker in the young objects. Those two effects are both an effect of the lower surface gravity. So if you have a lower surface gravity, you have a lower pressure in your atmosphere, and you get less pressure broadening of your lines, and you also get less collision-induced absorption of the H2 molecule. And this second effect is mostly responsible for this very different shape here in the H band. So here you see a combined effect of iron hydride, water absorption, and collision-induced absorption of H2. But in the young object, you almost only see the water absorption, which has this very triangular shape. So if I take the same figure that I showed you and overplot some of the known exoplanets on it, you can see that they fall mainly in the same sequence as the known young brown dwarfs, and some of them even fall further down to fainter magnitudes than all of the known young brown dwarfs. So for example, the very popular HR 8799 planets look like they are extending the sequence of known young objects. So as of right now, we don't really have many young objects across this drastic change here, which we call the LT transition. So it's going to be very interesting to try and characterize this for young objects. Here I'm showing you a final comparison between brown dwarfs and planets. So those are spectra that are overlaid one on the top of each other, but the black one here is a very old brown dwarf, and all the other ones in between are slightly younger and younger brown dwarfs, and the reddest one that you see here is a known exoplanet. So this is a wide companion to a young star in the TW Hydra Association. So one thing that I want to show you is that their features are very similar. So the young brown dwarfs and exoplanets have a lot in common, a lot of the similar molecules, temperatures. The main difference is the surface gravity. So this is like the difference between young and old brown dwarfs. Exoplanets have much lower surface gravity because they have much lower masses. And in addition to that, most of the known directly imaged exoplanets are also young. So that makes them very similar to the young brown dwarfs. And now the moving groups are ensembles of stars that form together around the same time and from a single molecular cloud. They're not extremely young, they're older than, say, 5 million years. So this gave them time to start spreading out and get rid of all the interstellar material. So you don't have reddening, you have groups of stars that are very, very wide in spatial position, but they still have consistent velocities through the galaxy. So they all move approximately in the same direction.
I'm sorry, what is this plot?
Sorry?
What is this plot? What are the green lines and the other
Yeah,
ones?
okay, I'm going to explain that in a
okay.
few seconds. So if you take a group like that spans a very large spatial extent, and you place yourself on the Earth and look at the velocities of all these stars, they're going to fall everywhere on the celestial sphere. So this is an example of known members and candidate members in red and green. So all the arrows are the positions of the members on the sky. You can see that they're almost everywhere across the sky. But if you plot their proper motion, so this is their lateral motion that we see from the Earth, they all converge to a point that's called the apex here. And this is actually an effect of having all the same velocity in the galactic referential. So it's really an effect of projection on our sphere that they have different proper motions, but they still all converge to the same point. And this convergence has been used for a while to find new members. So we try to find objects that have proper motions that converge to the same point. So most of the members of these moving groups, they were found with the Hipparcos mission that measured the distance of a large ensemble of very bright stars. The reason for this is that if you really want to pin down an object and call it a member, you need its position, its proper motion, you need its distance, and you also need its radial velocity, so the velocity along the line of sight. So then you can transform all of these observables into the position and velocity in the reference frame of the galaxy, and then you can really call an object a member. So for this same reason, the brown dwarf population has been largely missing until the very recent years. So take out of this is that moving groups are groups of very close by objects that are young. So they're very nice places to search for young brown dwarfs. So when I started my PhD, it was very hard to find a new brown dwarf in a moving group because we did not have large data sets with known distances and radial velocities. So we had to find a way to prioritize objects and only get these measurements on a few brown dwarfs because they are very hard to obtain. You need a large baseline or a large telescope to measure these things. So what I did is I used the Bayes theorem to calculate the probability that a given star is a member of a moving group without knowing the radial velocity and distance. So this way you can actually not follow any star that has no chance of being a moving group member. You can only focus on those that could be members. So these two parameters, the radial velocity and distance, they are what we call marginalized. So we try all the values and then we integrate over the probabilities for all values. So this is Bayes' theorem. So probability of A given B is probability of B given A times a prior term and a normalization term. So this is what I used to transform the observables into a probability that an object is a member of a moving group. So really the advantage of this is to start with a very large data set and end up with only 1% or 0.5% of the total objects that you are actually interested in following up. So when I had this tool completed, I started a survey, which is called the Banyan All-Sky Survey. So the statistical tool is called Banyan. So this makes the BASS acronym. The BASS survey, I initiated it to try and find these missing young brown dwarfs in the moving groups. So I was targeting objects that are nearby, isolated, so I'm not speaking of companions to bright stars, and objects that are young, obviously, because they're members of moving groups. So the method that I used is to start from two very large area catalogs in the near infrared. Oh, I just realized there's something missing, but it's going to be okay. So I use these two very large data sets of objects. They're not just brown dwarfs, they can be stars or anything. So those are just all sky surveys in the near infrared. But they have this characteristic which is very, very useful. They were taken 11 years apart. So I can actually use that to measure the motion of individual objects in the catalogs. So this is what I did. I applied some color filters to concentrate on objects that have colors of brown dwarfs, and then I got their proper motions. I used the Banyan tool to target the ones that were the most interesting, and then I went at the telescope and got spectroscopy of these objects. And it worked very well. I found several new brown dwarfs, especially young brown dwarfs, by doing this. So all these objects in this plot are young brown dwarfs, and those two. So this gave us a very large boost in the population of non-brown dwarfs by almost a factor 2. So this opens up the possibility of having a really statistically significant population that you can study. So here I'm showing the spectral types of the objects that we knew before this survey in green, and in orange the new young objects that we discovered in this survey. So you can see it's a very large fraction. This missing spectral type here is completely artificial. We're lacking a good template to make the classification. So this is going to fill up in the coming years. A few objects from here and here are going to fall there. One of the very interesting things that this survey showed us is that in one of the moving groups, which is called Tucana Horologium, there seem to be too many objects with a mass around 13 times the mass of Jupiter. Why that mass in particular? It's just the selection effect. So the fainter objects, the lower mass objects, were too faint for me to find them in this survey. And the more massive objects were just less priority in my follow-up. So those are not completely observed in my sample. So what you get is just a window here where you have a very good recovery rate of the members. And I was surprised by how many we actually found. So it's something like 16 objects in this range between 10 to 15 Jupiter masses. And when we saw this, I actually sat down and looked at the typical IMF and how many objects would you think there would be in this range if you anchor your IMF on the massive population of this moving group. And the answer was that we're finding 36 times too many. So this is very intriguing. So there are many possible reasons for this. So one of the reasons that it's not possible is that they're not young brown dwarfs. So we have all confirmed them with spectroscopy. They're all young brown dwarfs. We know it cannot just be small number statistics. We carried out the Poisson errors, and it's a very significant overdensity. However, they could be members of different moving groups because we still don't have all the measurements to place them exactly on a velocity plot. So they could be contaminants from other groups. Maybe this association just happens to have a weird IMF. And then the last hypothesis, there's also maybe we're missing some of the massive members in Tucana. This seems quite unlikely because they would be in Hipparchus, and there's no strong reason for us to have missed them. So, and then the last hypothesis, I intentionally put it last because it seems less likely. It's like this happy ending hypothesis that you would like. Maybe this could be the start of a population of ejected planets. And if this were true, when we get here and start finding objects, when we start being sensitive to the lower masses, we would expect a rise if this were true. Because this 13 Jupiter mass is very massive for an exoplanet.
Jonathan,
Yeah.
are there other moving groups that have weird IMFs? Like how unlikely is that possibility?
In the nearby moving groups, we don't have very good IMFs for now, and I think this is true for all the associations still. They're either very far, so it's very hard to make a spectroscopic confirmation of the objects, or either they're so close by that they're everywhere in the sky and they're super hard to find. So this moving group Tucana is right at the sweet spot in distance, where it's not as spread out on the sky, but their members are still pretty bright. So this is the only one where I can really do a spectroscopic follow-up of these kind of objects to a significant basis. Yeah?
You said you deliberately were not looking for companions to stars in moving
Yeah.
groups.
Mm-hmm.
But if you have a funny IMF, wouldn't you expect to have a large number of brown dwarf companions to some of your stars in the moving group?
So this is still unclear. If we really want to know the total brown dwarf population, including all the companions, we're going to have to do direct imaging around all the stars. And some other teams are doing that. It's really a lot of work. So I haven't tried this. But something I did is look for very wide pairs. So when I find an isolated young brown dwarf, I look around in the 2MASS and WISE catalogs and look if I see any star that is close by and has the same proper motion. If this is true, then they could be common proper motion pairs. So those are very wide binary-like objects. So I did that for the objects that we found in this survey, and we only found a few of those. So all of these objects that we're finding in this group, all of this overdensity, are all isolated young brown dwarfs. They could be binary young brown dwarfs though, but this is also going to take a lot of observations to figure out. So there were some new developments on this side. So we've now gotten spectra, high resolution spectra with fire at Magellan for 11 out of 16 of these objects, and 10 of them match Tucana horologia. Only one is either a member of another group or just something that randomly fell there. But it seems very unlikely at this point that the moving group contamination hypothesis is the right hypothesis. So we're going to see when we find lower mass objects whether this still holds. So to summarize, the BASS survey consisted of a cross-match of the high-quality photometry sources in 2MASS and AllWise, two all-sky catalogs, and this yielded a twofold increase in the number of young brown dwarfs in the solar neighborhood. So, as you can see in the spectral type plot that I showed you, we didn't find many objects with spectral types later than L5. So this is consistent with the picture I showed you of the absolute color, absolute magnitude versus color, where we still don't have an LT transition for the young objects. So what I want to do now is go to these cooler temperatures and lower masses and try to find both the IMF at these lower masses and understand their photometric and spectroscopic properties. So the reason why we missed these cooler objects in the initial survey was that we applied several color cuts and quality selection criteria that required the sources to have good photometry in 2MASS. But the cooler ones are going to be so faint that you're not going to get a good entry in the 2MASS catalog. So you have to relax this if you want to find the cooler objects. So the goals of this survey are going to be to find a few Jupiter mass objects, so very, very low masses, and get high quality spectra for those. Those are going to be very nice complements for the GPI and SPHERE direct imaging campaigns. So they're finding young, very cold objects, but they have no empirical data to compare them to, except for young, old brown dwarfs right now. So I'm going to target this space here in age versus temperature diagram. So these green stars here are all objects from the BASS survey, so my PhD. And you can see that we have only a few known objects in this young age and low temperature. Those are mostly companions, so planetary mass companions. And the transition to LT spectral types, where the colors go to the blue all of a sudden, it's not very well constrained at these young ages. It could happen anywhere in that yellow region. So finding new object is gonna it's gonna like shorten this region and constrain it better. We know that the LT transition is likely to happen at cooler temperatures for younger objects. The only young objects that we know of all seem to have colder temperatures than the old objects at the same spectral type. So at a fixed spectral type. If you just take the spectra, compare them visually, and type them this way, you're going to call an L4, for example, an object that is cooler if it's a young one. So this transition where the clouds disappear, we expect it to happen at cooler temperatures than what is seen for the field brown dwarfs. There's another aspect that we're going to tackle to do better than the BASS survey regarding the algorithm to classify the members, the stars, as candidate members. So one of the problems we had with the Banyan tool, which I used for the BASS survey, is that it's quite slow. It takes around 3 seconds per object to derive a membership probability. So the reason for that is that we have to do numerical integrals, or we could also use Markov chain Monte Carlo, but we have some numerical solving to do because we don't know the radial velocity and distance. And I realized that these integrals were actually solvable analytically. This is quite rare. That you have a Bayesian problem that you can solve, but this is one of those, so this is a very happy coincidence. So we can actually calculate membership probabilities in a much faster way. So the CPU time went down from a few weeks to 1 minute for my PhD project with this new tool. So this is going to be very important because I'm now going to focus on much larger data sets than what I did during my PhD. So because I'm relaxing some quality criteria, I'm going to have many more objects to calculate probabilities from. Also, another aspect I want to improve in this tool is the inclusion of more moving groups. So we had 7 moving groups that were modeled in the previous version of the tool, and now we have around 17 moving groups. Some of those more distant, some of those are slightly older. But this is gonna increase our chances of successfully finding these young and cold objects. As I mentioned, I'm also gonna use several more catalogs of infrared data. So just to summarize all of this, those are the 5 steps that I want to tackle in order to beat this BASS survey, to do better than it. And all those in red are fixed now. So I now have a better tool to calculate membership probabilities, and I'll have access to a larger telescope in the southern hemisphere, Magellan. And I now have a cross-matching algorithm that is more more relaxed on the side of selection criteria. So the only things that remain to be implemented are more input catalogs and more moving groups, but we already have a large set of candidates from only these 3 modifications. Here I'm showing you a model of one of these moving groups, Tucana horologium, and I want to show you one of the other new aspects in this new tool. So those here, the X, Y, Z, are the galactic positions, so the position of a star in the frame of the galaxy, and the UVW is the velocity in the frame of the galaxy. So if you plot the known members in all these combinations, you can see that there are strong correlations between some spatial and dynamic coordinates. So in this example, objects that have larger positions in this z-plane have a larger velocity in the u-plane. And you can also see this correlation in a few other spatial dynamic terms. And this is something that the previous tool completely ignored. And this new tool accounts for that when it calculates the probabilities. So the result of this is that we're going to have a lesser number of false positives. We have a better constraint around the members of a moving groups. So I'm going to show you a few results from this survey. Here I'm showing you the old brown dwarfs in the same plot than earlier, and some of the known young objects. I put several planets in there and some new objects. Here there's a publication that just came out like 2 months ago that found some new candidates in this region. So those are very brand new. And here are all of the candidates that we have so far. So remember, I did not apply color and quality cuts, so it's expected that they're going to fall everywhere. And I want this because I don't know for sure where they should fall. So I want to follow them spectroscopically and only focus on the young brown dwarfs in the next step. It is actually expected that the younger objects will fall lower than the field sequence, like most of our targets do, if you assume that the LT transition happens at cooler temperatures for young brown dwarfs. So this is a toy model that Samo and Marley did to see what would be the effect of just changing the temperature of the LT transition. And the effect is that they follow a sequence to lower absolute magnitudes. So here I'm showing you the subset of objects for which we have spectra and that look like brown dwarfs. So all these objects are not distant contaminants or stars or anything, they're all brown dwarfs. And the next step, which is almost the final step, is obtaining a radial velocity for these objects to confirm that they're members of groups. So we've obtained radial velocities for 8 stars right now, and it happens that 5 of those had different radial velocities, so they're not members of groups, but 3 of them have consistent RVs. And 2 of those are members, candidate members still, to the very young association TW Hydra. So those are very exciting. They have a predicted mass of 6 times the mass of Jupiter. And this one here is even more exciting. It looks like a twin to the new exoplanet 51 Erie B, but an isolated version. Same age, same color, same magnitude, and it's same spectral type. So its mass would be 2 or 3 times that of Jupiter. So the only remaining measurement on this object is a parallax, so a distance. And when we have this, if it matches the moving group, this is going to be a very, very exciting object. So the telescopes I use, as I said, to obtain these measurements are the Magellan BAD, is the Magellan BAD with fire. So I'm using the prism mode to reject contaminants, like distant galaxies or things like that, and the Echelle mode to measure radial velocities. And at the same time as I'm doing this, I'm actually building a very high signal-to-noise spectral library for these objects. Because now that I have, when I confirm an object, I automatically have a very nice spectrum of it. One of the first discoveries that we made with this project is this object. So its name is pretty ugly, but this is an object that has been known as a brown dwarf for a long time, since 2004. And the authors of that paper noticed that it had some weird features that could be linked with a younger age and a low surface gravity. And the others actually say in the abstract, maybe it could be a 10 Jupiter mass object, a very young object, but we don't have any example of this or any strong evidence other than weird features in the spectrum. So I then noticed that it has kinematics very similar to Abidor, which exactly happens to match the age estimate that they gave. And the distance was also measured in the literature and also matched Abidor. Abidor is one of the moving groups. So all we had to obtain is a radial velocity, which we did with fire, and it did match Abidordus. So this is the latest type member of a moving group known to date. When I say member, I'm speaking of confirmed members with all of the measurements. So this is a T5 object with strong methane absorption. And one of the things that this shows us is that if you have only a low resolution spectrum of a cold object like this, it seems very hard to tell whether it's young or not. So you need high resolution like fire echelle and look at the absorption lines, individual absorption lines, to actually get a sense of if it seems to have a low gravity. So this is the RV measurement when I plot it in the UVW space compared with the members. So here I drew the 1 sigma ellipse around the members, so you can see it's in the locus of all the known members. And yeah, you can actually use this new object to make a tentative sequence of high likelihood members of Abidor at several different temperatures. And it looks like it's following the field sequence, but to redder colors and then fainter magnitudes. This particular moving group is 125 million years old. So this is one of the oldest moving groups in our data set. And it's expected that a few 100 million years after this age, they're going to actually fall on the field sequence. So it's expected that they won't be so different than the field sequence. So we still don't know what happens at 40 or 20 million years. This is 125. So another object that we found, as I mentioned, is a new member of TW Hydra that is young and super red. Its predicted distance is quite close, 25 parsec, and its mass would be 6 times that of Jupiter. So it's both the nearest known member of TW Hydra and also the brightest known isolated object that has the mass of a planet. So it's a very nice template object. So you can see in XYZ space, TW Hydra looks like a long filament, and the sun is somewhere around here, so us. And the object is on the closer edge of TW Hydra. If you plot it in UVW space, so we use the radial velocity with fire. This is the fit to the spectrum that gave us a radial velocity. And then you can place it on a UVW diagram and you see that it falls right within the known members of TW Hydra. So now I have like a few super exciting objects that I have, but I won't have time to go through all of them. But just to say, we already have a lot of super exciting objects with weird spectra, but we're sure they're brown dwarfs. Several of them are super red, which is a very good sign for youth. And their estimated masses go all the way down to 4 or 3 Jupiter masses. This is the super exciting object that looks like the planet 51 Eridani. So, and we have also found some exciting potential binaries. So those could be combinations of cool, very cool, and warmer objects. Those, when we have all their measurements, if they're confirmed members of the moving groups, they're going to be very powerful templates, because if you have a binary star, you know they have the same age, same metallicity, and then if you know it's a member of a moving group, you actually know that age. So you can constrain the models much better with the binaries. So several of them. So to wrap up the BASS-Ultracool survey, we used more catalogs, less filters, and better tools. And this already yielded a ton of new exciting objects. And there are many more to come. So, as a conclusion to all of this, we know that there are still a ton of very interesting objects to be found out there. There's actually a new paper that came out yesterday that's super interesting, showing that all of the very low mass and cold brown dwarfs within 6 parsec are highly different from a uniform distribution, which means that we miss a lot of ground dwarfs. We are still far from complete in our ground dwarf census, even at the old ages. And this is just because they're extremely faint. So these objects will be very useful benchmarks for atmosphere studies and direct imaging, and they will also be crucial to understand the initial mass function at these very low masses. So here I'm just showing you some of the upcoming papers that you can expect to see in a few weeks or a few months, and I'm going to conclude with that. So thank you very much. Questions?
So on your plot with the horizontal trend that you keep showing the magnitude versus, go back to the one you just had.
Sorry, just slow.
Oh yeah. It looked like after you started applying cuts, you still had one viable candidate that was sort of up on its own above the trend, one of those three.
Yeah.
Are you going to get data on that? Is that still
Wait.
a real star?
It's very weird. It's definitely weird because you could say maybe it's a binary, but this would move it by 0.7 in that diagram, and this is like 14.5 and 13, so you have like 1.5. You would need like 5 objects to account for that. It's not, doesn't work. So it's very weird. It did survive the cut where I obtained a spectrum and realized it's a brown dwarf. It's not a background contaminant, but I still don't have the radial velocity and distance of this object. So my guess is that it's probably not going to be a member, but you want to be sure. So you want to actually get a measurement, because we
would
could...
that just be, it would be closer so that...
It wouldn't account for that, because this is an absolute magnitude. So this would mean that at a fixed distance, it's much brighter than expected. So this goes against all of our expectations.
We
But-
don't know the distance, right?
That's
So it could
what I was
be-
asking.
Oh yeah. This distance I'm using there is the distance that best matches the most probable moving group.
Right, that's what I was
So yeah, so if it's not a member of the moving group, maybe it's just much closer than this distance, and it's actually fainter and in the field sequence. That's what I think is the most likely hypothesis. But you still want to check, because very often nature produces stuff that you didn't expect, so you don't want to make too many assumptions. Other questions? Yes?
So, in the moving group where you found, 30 odd times more random
Yeah.
mass objects than you expected,
Yeah.
compared to the initial mass function, where does that initial mass function come from?
This comes from, it's just a log normal distribution, which is anchored on the very massive objects, so the objects more massive than the mass of the sun, for example. So we expect these objects to be all discovered in this group. So you expect the group to be, the IMF to be complete at masses larger than 1 times that of the sun. So if you place a log normal initial mass function on and you anchor it on these massive stars and you follow the tail, then you can actually integrate from 12 to 14 times the mass of Jupiter, and you can make a prediction of how many objects you would expect if the moving group has a log normal distribution. And this distribution is what is found for all of the more distant groups, for the best data that we have on the field. So they all roughly match this this log normal distribution. When I say roughly, there are some discrepancies, but we've never seen like discrepancies as huge as 36 times. So it seems very, very weird.
So they match even at these very low masses, so they're not extrapolations, but the log normal distribution is based on real data at that point?
Yeah, the log normal distribution is not well calibrated at these low masses, and this is one of the reasons why I want to do this. It's to calibrate it. So it's totally possible that it breaks down at these low masses, but if it does, you would need a physical explanation for that. Because if you just expect what we know about the formation of stars in molecular clouds, and you just form them at random, it seems very, very unlikely to have a bump like this at the low masses.
Yeah, I'm still here. You might be able to test it.
Yeah, so I guess Alan would say that 13 times the mass of Jupiter is very massive if you expect them to be ejected planets. If you want to eject a planet, you need another planet that's more massive, typically. So, I don't know.
It's actually even too large for the microlensing results, right? Which
Yeah.
suggests that there's
Yeah.
only a factor of 2 excess, not
Yeah.
a factor of...
No. Actually, it's the microlensing result is way, way larger than this.
Oh,
So she's referring to Sumi et al. 2012. It's a Nature paper that's very recent. So they found a few microlensing events and used that to derive the density of objects, of very low mass objects. And they were actually sensitive to 1 Jupiter mass object, so way less massive than what I have. And they found that the most likely density of 1 Jupiter mass objects isolated in the field was twice as large as main sequence stars. So this is, instead of having like a log normal distribution, you have something that goes up to twice as large as the stars on the low mass scale. So this is completely unexpected, and it's much more significant an effect than what I'm finding. So I don't remember the number. I've carried out the numbers at some point, but if I remember well, it's something like 200 instead of 36 times. It's way too large.
Larry was here.
I had another quick, which is going back to the, this bump, the 13 Jupiter masses. You said one of your possibilities was that they might be contaminants from other moving groups, but would there be some reason to expect the contaminants to be weighted towards the lower mass ones and not also sample the IMF?
That's, well, there would be an argument for that, which is that the most massive objects have distances and radial velocities. So they're not likely to be contaminants, whereas we only have proper motion and sky position. So that's why I was thinking they could be actually other objects just mimicking their properties. But now it seems unlikely because it's very hard to mimic proper motion and radial velocity. Distance is really gonna conclude this hypothesis, but I find it very unlikely that this is a good hypothesis. However, that maybe Tucana could be more than one group that just happened to sit at the same place, like in spatial and dynamic space. So that could cause a weird IMF. I don't know what can be the cause of this. I honestly think that this ejected planet hypothesis is not very likely, but it would be so exciting that you want to make sure.
Well, Jonathan will be here for another almost 3 years, so to take advantage of his great statistics knowledge, if you have Bayesian problems you need solved, I encourage you to go talk to him, and thank him for stuff.
Maybe you could give a seminar or a course in basic statistics and market change. All the stuff that I very much